All right, so we're going to start talking today in section 2.2 about describing sets. And we won't finish today, we'll finish it next class period if there's work then. But to start with talking about sets, all a set is a collection of objects. Okay? It doesn't even have to be objects per se. So it could be a collection of people. They're not really objects, right? It could be a collection of CDs. Do you guys know what a CD is? That's good. It could be a collection of food, it could be a collection of anything, okay? A collection of shoes, okay? So any kind of collection of objects. The items that are in that collection are called elements. They're the elements of the set. So if I described a set as the people in my family, if you write this down, the people in your family, then the elements would be each of the individual people. So I would say my husband, I would say my daughter, and I would say myself, and I would say my son. Right? So that would be the elements of my set. There are two methods that are most commonly used for describing sets. Okay, so one of them is the listing method. So that would be where I list all of the individual elements out. And that's really great if they're a small set, right? So if I wanted to list out the people in my family, that's fine. There's only 4 people in my family. If I was one of those other people, this might be a long list. So there's also the same kind of thing happens when you talk about numbers, right? If I wanted to list out all the counting numbers, not only would that be a long list, it would be an impossible list to write because I never stop with writing that list, right? I can always keep counting numbers up, so that's sort of problematic, which means that we can't always use the listing method that is not in its entirety. We can put the ... dots on the end, but there's other methods. So the other method is called set builder notation. So let me, or set builder method. So let me talk about what that method looks like first. So let's say that we had, well, let me just show you what the method first starts at. You start with a curly brace, and you write an X, and then you write a bar. And then right in here, you describe what X is. And then you close it off with a curly brace. We're going to do one more word, but this is what it looks like. And when I see this, it's read as X, that bar is read as such that. I said it's all X, such that, and then this description follows. I want to talk about some common notations used in set builder notation because your book uses them. And I'm not sure how familiar you guys might be with those notations, so you need to know if you encounter them, what they are. And then if you want to use them, of course, you can use them then. The first symbol is this symbol. And this symbol means is an element of. Okay? So we can say 5 is an element of the counting numbers. That's fine. There are some sets of numbers I'm going to write next. So I'm going to start with the smallest sort of set of numbers. So when you first learn to count, you use the counting numbers, which means you start with the number 1, right? Small children, you ask them to count to 25, they don't start with -2. They start with 1, the counting numbers. So the counting numbers are also called the natural numbers because they are what we naturally count with. So this symbol is an N with a double line on the left. This is the natural numbers. And these are the numbers that are 1, 2, 3, ... Very shortly after you start learning to count, somebody says something to you like, I have 3 apples and I give all 3 apples away. How many apples do I have left? And you say 0, but that wasn't included in that original list, was it? So you've somehow introduced a new number into the mix. And you've introduced a new type of number. They're called whole numbers. This is a W with a double line on the left. These are my whole numbers. And they're the same as the natural numbers, but they include the number 0 as well. Those are my whole numbers. Okay, and someone does something really creative. My husband did this to my daughter yesterday. Seriously. In my office, he wrote a board. He wrote something like, and he did a 3-digit number, and I know that's fine, but he wrote something like 975 minus 976. She said, all right, that's what she said. What do I need in order to be able to do that problem? I need negative numbers, don't I? The answer is -1. So I need some negative numbers. And if we introduce negative numbers into this discussion, we have what are called the integers, and that's a z with a double line in the middle. I'm going to ask me, I think, I could totally be wrong on this, but I think it has to do with the Latin word for integers. Even if it doesn't, that's what it's just pretty stupid. So these are the numbers, so they have dot, dot, dots on either side. So this would be -3, -2, -1, 0, 1, 2, 3. So they include all the numbers you've already got before. All of those are already integers. Plus they include the negations of them, the negative parts of them. So those are integers. I'm going to show you just a couple more because they're the only other ones that I think you'll see. This is supposed to be a Q with a double line on the left, or an external, or a line in the middle on the left. These are the rational numbers. Rational numbers are your fractions, or anything that can be written as a fraction. So all the numbers up till now are rational numbers. Take it number 3. It's rational. I can write it as a fraction, 3 1. It's not a very exciting fraction, right? But it can be written like that. So I can write it as a fraction, 3/1, with integers on top, integers on bottom, so it's a rational number. So the key idea that you want to be thinking of here is the fractions are now included. Okay, so you get everything we already had plus fractions, legitimate fractions, like ones that really look like fractions, like 1/2. Okay, those ones. And then the last one that I want you to be aware of is R with the double line on the left. And these are real numbers. And the items that you get to now include are numbers like square root 2. So let me actually do it this way. Let's say radicals, pi, e, etc. are now included. So all the numbers I wrote prior to this are also real numbers. They're real numbers. So the only number that you've encountered, and you may or may not have encountered in the oral math classes you have, it's not a real number, it's realized. You know? For I. Okay, if you don't know what I'm talking about, okay, you don't have to. But if you have encountered the number I before, that is the only number that you have encountered that is not a real number. We call it an imaginary number, and we don't call it imaginary because it doesn't exist. Like your imaginary friend, okay? Terrible, terrible language was chosen by somebody, but it wasn't me. So I will not take blame for that. But they call them imaginary numbers. So all the real numbers are probably almost all the numbers you've ever worked with. Yes. E is a number that you usually see used in compounding, things like compound interest or things that grow exponentially. It's about 2.718. But it's, again, like pi, it doesn't have a repeating form of a number at the end. It has unlimited digits and things like that come on top. So pi's got the same issue, right? Pi is not 3.14. It isn't. Promise it is not 3.14. That's a great approximation for it, but that is not pi. Okay? It has this sort of unrepeating, no way of writing it in a smaller form kind of thing. We can approximate it if we keep writing closed forms for pi. Every now and then you hear something about some crazy person memorizing the first 1,000 digits of pi or something. Really? It's time for that. But people do this kind of stuff. Okay, so these are the real numbers. What I want you to know is I want you to know this notation in case you need to use it or in case you see it used. Okay, because you will see it used from time to time. So I'm going to show you, let me show you one other thing from what I did. If I put these inside of curly braces, what I've done is I've actually done the listing method for each of these sets. Okay, I didn't do a listing method on Q and R. There's not a way to write it that way. So, but those would be the listing method for each of these. Okay, so let's take a look at the next slide. It says write the set of all natural numbers less than 5 using, and we're going to use these two methods. So, what are all the numbers that are natural numbers less than 5? 1, 2, 3, 4. Yeah. So I start with curly brace. and I write them out. 1, 2, 3, and 4. And I do not include 5, right? If your math class is really still struggling with this concept, that if it says less than, that doesn't mean equal to. It really means less than, okay? They want you to say less than or equal to, they'll say it. It really is less than. 5 is not included, not get included. Okay, so I wanted to show you an example of what step element notation then looks like, okay? So this is fine for this one, right? There's nothing wrong with this. It's easy, it's simple. I don't have to think too much to write it out. It's not a long process. It's great. But that doesn't work for all numbers, so I need to show you another option for those cases in particular when it wouldn't work, but I'm going to show it with this case that the first one was fine for, okay? So you do a curly brace, you write an X, and you do a bar. And it always starts that way. If you can get no further, you can get that bar. The next thing you do is you describe what X is. In the order of what I'm about to write doesn't matter. There's 2 statements about X up there. What's one of them? It's a natural number. It's got to be included in what I'm about to write down. What's the other one? It's less than 5. So you guys said natural number first, so that's what I'm going to write first. This is X is an element of the natural numbers. Okay. X element natural numbers. Shorthand notation, if you see what you write out, X is an element of the natural numbers. Well, okay. Now, what's the shorthand notation for giving me from having to write X is less than 5? Use the less than sign, right? So there's going to kind of be a comma here, and we do less than 5. Those are curly brace again, and then that is the set builder notation for this solution. Make sense?
So could you write it out, or do you want it to be special?
Oh, you mean like where the X is a natural number? You can write it out, but I will guarantee there are points where your book will write that notation presently and then you'll be able to know what it says. So yeah, but if you wrote it all out, that would be okay. It wouldn't be wrong. That's okay. That's okay. I don't care. But if I write out this, you need to know what it says. So whatever it takes for you to at that point to be able to read it and digest what I told you. Okay. All right. Next thing we're going to talk about is equal sets. Equal sets are sets that are exactly the same. Well, that's what seems obvious, right? But equal is exactly the same elements in the set. We also have something called equivalent sets. So equivalent sets, I'll jump back up to the one I wanted in a minute, but equivalent sets are not the same as equal sets. It's sort of weird because in our language, we say that word equal and equivalent, so they mean the same thing, right? They're slightly different in this context, okay? And it's hinged upon this idea of a one-to-one correspondence. So a one-to-one correspondence is simply a pairing of elements between 2 sets where one item in one set is paired with one item in another set. Okay? So I'm going to draw you a picture. This is a picture of a set. It's just a circle and it's got 3 items in it. It's got the numbers 1, 2, and 3. And then we've got another circle over here and it has 3 items in it. It's got X, Q, and R. One-to-one correspondence literally means that I can draw a line from this number 1 to some item in this other set. I can pair this up, this 2 up with something here, and this 3 up with something here. And when I'm done, there is a 1-to-1 relationship. Every item in the first set goes to one item in the second set, and no more, and vice versa. We can go backwards the same way. Okay, one line between 2 items. So equivalent sets are sets that have this relationship. What this boils down to is that 2 sets are equivalent when they have the same number of items in them, right? Because as long as I have the same number of items here as I do here, I should be able to draw all these lines and make that work, right? This is the reason this is a problem when we get together with my sister. If I have 2 children and she has 3. You guys know this is a problem, right? Who gets to play with who? Somebody gets left out. Or somebody's mad and there's a group of 3 somewhere. There's not a one-to-one correspondence. We don't all have our one buddy. Okay, this one buddy sort of relationship, that's one-to-one correspondence. Those are equivalent sets that have that relationship. Now, we want to be able to, what are you saying? Okay. We want to be able to talk about how many one-to-one correspondences there could be. So this example is sort of hitting at that idea. right? So it says we have 2 sets with 6 elements. So there is a one-to-one correspondence, right? Because I have 6 items over here, I have 6 items over here, and I clearly could draw a line across, straight across if I want to, between one item here and one item here, and they all have a pair. But then the question is, how many of those pairs would I have? Right? Well, let's think about it like this. So let's take our set. Let me draw a picture for it, and then I'll do it another way too. Those of us who think visually can see my picture. Here's our one-to-one set. Here I have 1, 2, 3, 4, 5, 6, and I've got another set over here. I have, and I'll just do the first 6 letters of the alphabet: A, B, C, D, E, and F. All right. So just like we learned back in chapter 1, there's often more than one way of doing these problems, right? Well, more than one way of solving problems in general. So one thing I could do is I could take the number 1 and I could just count. Well, how many different people could number 1 be paired up with? 6, right? I have 6 different people that number, or 6 different letters over here that number 1 could be paired up with. But once I make that determination, once I say 6 goes with A, whatever, not 6, yeah, 6 of us. Number 6 goes with letter A. Once I make that determination, then the next letter does not have 6 people he can be paired up with any longer. One of them has been taken. Yeah? Okay. So once my daughter decides that she's going to hang out with my niece, if the 2 of them pair up, there's no other correspondence that can be taken if I'm trying to pair them up 1 and 1. So there are 6 people, so I'm going to do it from here now. This is my first number. There are 6 different people that the first person walks in the room. So imagine there's 6 people in this room, and there's 6 people in the hallway. So this is a mixer. There's boys in the room, there's girls in the hallway. This first one comes in, okay, there's 6 boys. This wouldn't happen at OU, right? Boys for this. Okay. So one girl walks in, and she picks out her boy, and she takes him out of the room. She had 6 choices. Okay? Boy or girl number 2, she walks in, she does not have 6 choices anymore. She has 5. There are 5 choices left that she gets to make. And the pair walk off and have fun or whatever. Girl number 3, she walks in. How many choices does she get? 4. She has 4 choices left. She's still doing pretty good. Girl number 4 walks in. How many boys are still left in the room? 3. She has 3 choices. What are we on, 5? Girl number 5 walks into the room. It's 50-50 shot here, guys, right? She only has 2 choices left. And the poor lonely girl is in the hallway, is just thankful there's still somebody left in the room that she gets to take home. Or maybe take on a date or whatever. There's just 1 left though, right? 1 left. Yeah. There's just 1 left. She only has 1 choice when she's done. Okay. And you've probably seen a number written sort of like this before, right? Because what we're going to do is we're going to actually multiply these together. And if we multiply them together, you can grab a calculator if you want to. What do we get? 720. There are 720 different ways that those 6 boys and 6 girls could have paired up. Is it any wonder it's difficult to figure out which boy is the rightful way? Really? That's just a 6. I mean, really? Okay, so we have 720. Now, does anybody see this? 6, 5, 4, 3, 2, 1, 4. What is that? That's an exclamation point with this. If you haven't seen it before, it's okay. But this does have another shorthand notation. When you multiply a number out until it's down to 1, it's called factorial. This would be 6 factorial, and it's not 6 down excited. Okay? It's 6 factorial, which means 6 times 4 down to 1. That's what that means. So you may have seen it before if you haven't. It doesn't hurt anything, but this is the process. This is what we would do. Okay, cardinal number. All a cardinal number is the number of items in the set. Okay? So if I want the cardinal number for the people in my family, that's 4. My immediate family, I have 4 people in my family, right? It has a notation. It has an N and then it has parentheses, and inside of the parentheses is the set. Okay? So we could write in parentheses, people in my family, close parentheses, and we can talk about that, and it'll be okay. The description for the set in between. We can use a name for the set, like they've got in this noted S. There are basically two types of sets, and then the third one is a special case. There are finite sets. So those are sets for which I can count. Now maybe a big count, I mean like maybe a million, okay? But there are sets that are actually able for me to count up and write down a closed number for them. Right? So if I said, stars in the sky, we can do that, right? God tells Abraham to count the stars in the sky. And if he could really do it, he had enough time to do it, that's a countable. Yeah, I can count those out. There's a number that is, right? But there's also things that are infinite, right? Things that you can't count. And I don't just mean like I don't have enough time to count them. I mean like it's not possible. Like if I told you to count all of the natural numbers have that dot, dot, dot at the end. They keep going on forever. There is no way to count them all because whatever you tell me is the last one, I just add one to it and I got one more, right? That's an infinite set, something that doesn't have a way to actually write down a number for how many items are in it. The last example is actually an example of a finite set. It's just a very uninteresting finite set. It's the set that's called the null set or the empty set. So it's a set with nothing in it. And I know that sounds sort of odd. It has a notation. Let me put that first. The notation looks like a zero with a slash through it. So you may have had some math teacher along the way tell you something about not putting slashes through your zeros. I know that some of you don't because I often will get freshmen. I know you guys usually aren't freshmen. I'll often get freshmen in and they will write all their zeros with a slash through. And I have to say on their first assignment, you can't write a zero that way. That's another notation. It means something different. And it means a couple of something different. You've seen it before and that would mean no solution, right? And here it's going to mean in set theory, which we're looking at right now, it's going to mean the null set or the empty set. And sometimes also, you'll see it written like this, curly braces with nothing inside, which is very intuitive. It's a good descriptor, right? Visually, it looks like exactly what it is. But what I don't want you to do, and I'm going to write this on the board, and then I want you to put a big old X through it so you never do it, okay? It's one of those things in teaching they tell you to never do. To never write anything on the board that's wrong. Make sure you cross it out. It is inappropriate to write a set notation as an empty set inside of a set. Okay, that does not mean the same thing. So don't get the two notations combined. Choose one or choose the other. You don't combine them. Let me give you an example of an empty set because this sort of has the feeling of, you know what? Never mind. I'm going to use example 11 and have that in there. Okay. So we'll talk more about empty sets when we get to the last slide, which is not going to be today. All right, so let's take a look at some sets, and we're going to find the cardinal number for the sets. Again, cardinal number just means how many of them are in the set. And some of this looks like things we've seen, because we did this when we saw sequences, and we talked about it when we talked about Gauss. Remember, he added up a bunch of numbers. We had to figure out how many numbers he added up. So we're encountering that same kind of an idea again. So the first one we're going to look at, and let's just call each of these set A. And what we're finding on these is n of A, the number of items in set A. So the first set is from 9 to 99. How many items are there from 9 to 99? How many? 91. There are 91. And if you're looking at that and you sort of get cold feet on how many I'm supposed to be counting, the easiest way to think about it is, well, let's pretend it started at the number 1. How many numbers would there be from 1 to 99? 99 of them, right? But I don't have the numbers 1 through 8. How many numbers are there, numbers 1 through 8? 8, because those are the ones that got left out in my count, right? So I would have had 99 if I started at 1 and stopped at 99, but I don't have the first 8. So there are 91 items there. How about part B? How many are in, I'm sorry, yeah, part B, set, set A. How many of them are in that set? One thousand? And one, yes. Teamwork, right, ladies? Teamwork. All right, so again, let's think about what we would do. This does not have all the numbers, right, up to 2002. But let's pretend like it did. Pretend like it started at 1 and it went up to 2002. How many numbers do I have? 2002. But I don't actually have all of them. I only have the even ones. Right? That's half. So I would have had 2002 if they were all listed. But they're not all listed. I only have the even ones listed. And the same thing would happen if I went from 1 to 2001, right? Same idea. All right. The C looks a little different because it's that notation. It's not list notation. So this right here says that I have the set of x squared numbers where x is equal to 1, 3, 5, 7, 99. Okay. So the actual items in this set would be numbers like 1, 9, 25, 49, and I don't know what 99 squared is, but that's where we would end, right? And each one of the items squared. That's what this set looks like. If I were to write that set out for you, that'd be harder to look at than the set that they wrote. Because here's the deal. However many items there were in the set 199, odds, that's odds, I'm going to have the same number of items when I square them, aren't I? And it's easier when I look at that to count the numbers from 1 to 99 odds than it is to count the numbers 1, 9, 25, 49, and I have to have a really long list because my list would get really long. How many numbers are there from 1 to 99? Yes, the odd ones, there are 50. Now, this one's a little bit more awkward sort of to list. So think about this with me. If this had all the numbers from 1 to 99, what would I have? I have 99 of them, right? But I only have half of them in it. But if you divide 99 by 2, it's not a whole number. I obviously do not have 49 and a half numbers here. This can't have half of a number, right? So what's really going on? Well, what's really going on is if I went from 1 to 100, and I only look at the odd numbers, I'd still have the numbers from 1 to 99 odd numbers, wouldn't I? So it's kind of like on this one, that I have the numbers from 1 to 100, and then I took away the half of them that were the even ones. That would take away 100, right? The number 100. And I would be left with stopping at 99. So literally, you can either think about this as being the number 100 or as being this sort of idea that you rounded it up. And that's okay too. All right, we have one more left. All right, part D says, I want to find the number of items in my set A. These are all the items X, where X is equal to X plus 1. Somebody's going to have to figure out for me what X value would have that property. What number is equal to itself plus 1? Nothing. If I take any number and I add 1 to it, I can't get back to the number of terms, right? There are no numbers that have this property. There are numbers that have other properties, like I could say a number that's its own square. 1 is its own square, 1 squared is 1. That'd be okay. But this property doesn't hold. There is no number that when you take it and add another number 1 to it, you get the same number you started with. So this set actually is the empty set. And how many items are in the empty set? 0. Okay, when we're counting items, the answer needs to be a number answer, not the set it itself. So this is the set, the empty set. This is the empty set, that's not the question. The question asking how many items are in it. Okay? All right, we'll stop there today. Go ahead and get started if you can over the next couple days, and we'll finish it on